So next what we will do is we will see two more things, and that is the end of Lorentz group that we can do here. One thing is one more way of looking at Lorentz group. So far we saw that Lorentz group can be thought of as SO31 with the real generators L and K. Then you complexify and do some abracadabra, then it looks like SU2 cross SU2. We will now see a third way of representing Lorentz group, and that is as SL2C. So here the observation is that we introduce for any 3D vector, for any Lorentz 4 vector, like the energy moment, for example P0P, right, the 4 momentum of a particle. Introduce V matrix equal to V0 times identity plus V dot sigma or V dot tau, the physicist notation, which in full form is simply equal to, so V0 times identity, so the 0th component you put here, but then there is V3 times tau 3, so there is minus V3, plus V3 and minus V3, and then there is V1 minus I times V2 and V1 plus I times V2. So the matrix looks like this. Now the interesting thing is that if you take determinant of this matrix, then you actually get the Minkowski norm. So note det V is actually equal to, take the determinant, so you get this times this, which is V0 square minus V3 square, and this product is V1 squared plus V2 square but with minus sign. So essentially it is equal to V0 square minus the vector V mod square, the Minkowski norm. So we can see that this norm would be preserved provided we transform this by a unitary transformation. So right, because then determinant of u dagger would be equal to, with u unitary, then this would be fine. Or another way of looking at it is, if it is not unitary, then you would have found that it would become det u squared. So you can drop this for the time being, we will actually derive it. So suppose you propose this, then you will find that determinant u is product of the determinants of the other side, which is determinant of this times determinant of u dagger, but determinant of u dagger is just going to be star of the determinant of u because it's just star transpose. So it is mod squared of determinant u. Thus det u squared equal to 1, this equal to 1 is sufficient to ensure preservation of the norm but further to avoid getting changing sign of V0 and so on, V0, the zeroth component in 4 vectors is important because it is usually either the energy or the time or something, so you don't want to change its sign. So you require determinant u to be plus 1. It needs a little bit of calculation to check why this suffices, but I am skipping it for the time being. Thus require that determinant of u equal to 1. This is what we actually call, so all we started with was most general matrix u, 2 by 2 complex matrix u, and we transformed our representation v by u times dagger of that u. We didn't restrict any u that point up to that point, and the only restriction we have finally put is that determinant u is equal to plus 1. This is called the special linear group, the subgroup of GL2C. Makes the set of allowed u to be in SL2C. I mean, that is the definition. If you put no other restriction on 2 by 2 complex matrices of GL and C, so determinant should be non-zero, but the only restriction you put is you set the det u to plus 1, that is called SL2C, and therefore SL2C is one more realization of the Lorentz group as a group theory. Now there is something a little interesting as well. If you just change this sign V0 1 plus V dot tau, if you put minus V dot tau, also everything works, okay, because it will only change signs of V. So determinant will still come out the norm and so on. So we get two inequivalent SL2C representations of so I'll just make, in case you ever read more literature on this, and nowadays that the Majorana particles have become important to condensed matter physics. If you ever read two component formalism, but let us not mention it. So this is one more way of thinking about the Lorentz group. Okay. Essentially means a spinner, but spinner with some direction or something like that. Okay. So that is one remark about an additional way of looking at Lorentz group. And finally, I will end with talking about what is called as Clifford algebra. Okay, this is algebra of gamma matrices of the Dirac equation. So the thing is that Dirac invented this. This is one of the major applications of group theory to physics. So the last bit gets the most exciting because it was a puzzlement to a whole generation of physicists. So in 1929, Dirac formalism and Clifford algebra. So in 1929, Dirac proposed in modern form x0 is c times t and I gamma dot grad minus m psi equal to 0. This is Dirac equation, where Dirac proposed these matrices so that they have anti-commutation relations. Should I write it like this? Yeah, may as well once. Okay. So there is of course identity. There are 4 by 4 matrices. Times delta ij. So if you wrote out in detail gamma 0 squared, basically this is an anti-commutator. So it is gamma 0 plus gamma 0 gamma 0. So there is factor 2 anyway. It says gamma 0 squared equal to 1. This says that each of the gamma I squared is minus 1, minus the identity. And if you take gamma I with gamma j, so gamma 1 gamma 2 plus gamma 2 gamma 1 will be 0. Similarly, gamma 0 gamma 1 plus gamma 1 gamma 0 will be 0. So all together one writes this elegant notation: gamma nu anti-commutator equal to 2 times eta metric mu nu times the 4 by 4 identity matrix. Okay. So Dirac used slightly different notation, but this is what it is. So what is the utility of all this? The utility of this was that if you squared this operator, if you applied this operator another time, then you got a relativistic wave equation. D'Alembert. Okay, times the m square term plus the m square term. So now what this says is that if these matrices were 4 by 4, then this is a 4 component object. The psi is itself a 4 component object. Here it says that this is times an identity matrix. So each component psi obeys this wave equation. So this is sometimes called Klein-Gordon equation. But it should more correctly be called relativistic Schrodinger equation. So you might wonder why Schrodinger put I d by dt equal to minus grad square. The Schrodinger was not dumb. This was 1927. It was 20 years after special relativity. But when he did it, he didn't get the hydrogen lines correctly. So he had to fudge something. So he said, "Usko chhod do." He then applied the non-relativistic equation, got the hydrogen spectrum perfectly by using Laguerre polynomials and all this. End of the story. But in the end of that paper, Schrodinger says that ideally, however, we should be using the relativistic equation, and then leaves it at that. Later, Klein and Gordon got onto the job and they realized a lot of problems. First was that once you have this, you don't have conserved probability of Schrodinger equation. You get indefinite, you don't get a psi dagger psi conserved current. Okay, in Schrodinger non-relativistic theory, you take psi dagger psi and normalize it, but that's because psi dagger psi is a conserved density. Here you will not get any conserved density like that. So that is one problem of the wave equation. The other problem, which reason why Schrodinger missed using it, is because he was getting this j into j plus 1. And he kept thinking he had to put integer, but actually it was not integer, it was half integer, which he didn't know at that time. So if he had put half integers, he would have got it right. So anyway, this is called Klein-Gordon equation. Even Klein and Gordon basically got very puzzled by this equation and what it means and so on, because it was giving indefinite probability. So Mr. Dirac sat one day and said, how do I have an equation that is both relativistic and gives positive definite psi dagger psi? So he said, I remember that if I had Schrodinger equation with first order time derivative, I do get conserved current density, conserved density. So it has to be first order in time. But then by relativistic invariance, it should also be first order in space. And so put some coefficients here and then try to see how I recover the Klein-Gordon equation. And if you do it, then on squaring you have to anti-commute these to get the cross terms to drop out. Okay. So that's what Dirac did. And it so mystified everyone that nobody understood it for a couple of decades at least. And Dirac got from it both positive energies and negative energies. That happened, that you cannot avoid, the property that this had. So Dirac was bold enough to, this is what you have to give to Dirac. He said the negative energy states are all filled forever. And by then Fermi statistics was known. So he said each state can be occupied only once. So if the states, all the negative energy modes are fully filled, then nothing can go into it. So we are seeing only positive energy electrons. However, every once in a while, one of the negative energy states may get kicked up to a positive energy state, and then you will be left with a hole there in this filled up sea. So the hole, then he argued, would act like an oppositely charged particle of same mass. So you would have to have positrons, but he didn't know of any positrons existing. But he knew proton existed. So he said, well, if you allow me a factor 2000 mass difference between positive and negative charges, then I have a relativistic theory of electrons and protons. Okay. So this he proposed in 1929, and it was so surprising that Niels Bohr said that this was a good way for catching elephants in Africa, because you write Dirac's theory on a board, put it at the water hole of the elephants. When they read this theory, they'll be so stunned that you can put them in your truck and take them home. So, etc. And for several decades, people wondered what the hell this was. Well, it turns out it is just a representation of the Lorentz group, but couched in a different language. And the point was that this kind of, so one other way of thinking that people caught on to was that this gammas were in some sense the square root of this differential operator. Okay. That this differential operator, which was first order in the derivatives, was like a square root of this second order differential operator. And so the gammas were somehow a square root of the space-time metric, okay, because this involves minus dt square plus mod dx squared, and that can be seen here because we are saying that this I put eta mu nu, where remember our notation was eta 0 0 is plus, it is that Minkowski metric 1 minus 1 minus 1. So it tallies correctly with this if you put eta here. But now think of this as the metric, but the left hand side is quadratic in gammas. So the gammas are somehow taking a square root of the eta metric. So that was the main hint people had. Then the mathematicians, when they heard about it, they said, but physicists are a little slow, aren't they? Because almost 50 years earlier in mathematics, there was a man called Clifford who had identified this algebra which would take square root of the Pythagorean metric. For SON with metric delta, right, the delta ij, we can introduce gamma I gamma j equal to 2 times delta ij and times identity matrix of size 2 to the power n 2 to the power n by 2. Okay. Which is biggest integer smaller than. So for odd, for even n, we need n by 2 cross n by 2 matrices, and for so of course in 4 dimensions we want 4 dimensional matrices. Goes as powers of 2 to the 1, yeah, 4. So that's correct, 2 to the power 2. And for odd n, we and minus 1 by 2 times n minus 1 by 2 size matrices. The main connection between this and the group SON group which leaves the delta matrix invariant is that the rotation generators of SON denoted Mij with I equal to 1 to n. So remember this is rotation in the ij plane. We can show that in fact Mij are equal to 1/2 gamma I gamma j commutator. So how do we show this? Well, the statement is that you know the basic algebra of the gammas. You assemble the Mij out of these as products. So this commutator makes sure that you don't get any II. Okay, you only have 0, 1, 0, 2, 0. You don't have 0, 0. This commutator will obviate that. So there are exactly as many Mijs, as many commutators as there are Mijs, and you can compute the algebra of Mij. You will recover the algebra that I told you last time with Mij mkl. It should be delta ij delta times mkl. So the algebra of SON can be recovered from this by using the Clifford algebra of the gammas themselves. Okay, so let me just check. If we have 3 dimensions, then we still need 2 by 2 matrices, 2 to the power 1. So this is 2 to the power. That's what I was missing, wasn't it? 2 to the power. I wrote it here correctly, but I didn't. So 2 to the power 1, which is for dimension 3, 2 as well as 3. So sigma matrices will work, Pauli matrices will work in dimension 2 and dimension 3. The gamma matrices become 2 to the power 2 because 2 to the power 4 by 2. So 4 by 4 matrices are needed in 4 dimensions, but they will also work in 5 dimensions and so on. And what one can show is that the Mij exactly satisfy the SON algebra. Satisfy the Clifford algebra. So what Dirac had stumbled on was the Clifford algebra of the Lorentz group. Of course, with the big change that it was not delta ij but eta ij. So there is quite a few changes there are relative sign, minus signs and so on. But this is what essentially what the Dirac equation is. Okay, so I think we will stop with Lorentz group there.